Okay. And one final step here. Nice. I have to rework my schedule so I can get off a little bit earlier, get over here because this takes so long. It's weird how this kills that. Okay. All right. Hopefully we can see. And we're good to go here. Okay. So if we finished talking up about pressure, well, we didn't finish, but we talked about pressure on a surface, and we talked about how to find the pressure, and then, or how to calculate the maximum pressure, and how to find the location of the centroid, right? Remember, we're back up to speed. So two things that we do know about pressure on a inclined surface or a flat surface is the pressure force, where to find it, okay? So now we can apply some basic hydrostatics. Where my camera's at there. Okay, so hydrostatics. All right. This is, once again, nothing that you haven't seen before. In fact, this is something that you've probably seen multiple times. But we take the pressure equation, so use pressure equations, which, if you don't remember, we said that the pressure force, which is a vector, is equal to the pressure times the area, and the location of the pressure force, L sub P, which some books call Y sub P, it's just different notation, is equal to the location to the centroid along the inclined plane plus the area moment of inertia of the gate or the surface, excuse me, divided by L sub C times then the area. So once again, L sub C is the distance to centroid, and some books do call this Y sub P. Distance to the centroid along inclined plane. Oh, that's not showing up here. Let me back this out a little bit. Inclined plane. Okay. And A sub C is the area moment of inertia of the area. Okay. So now that we have those two equations, we can bring that and just apply it to a standard static scenario. What do I mean by that? Well, now we have our other equations that says that the sum of the forces in a given direction, so I'm going to say sum of the forces in the x direction is equal to 0. We could include some of the moments in the y and z direction also equals 0. So I'm just going to highlight both of those up there like that, just indicating that it's all three directions. And then the same thing is that the sum of the moments is equal to 0. So using basic static principles now, we can solve systems for forces like how strong do our bolts have to be, how strong does some objects that's holding the gate what size of a shaft do we need to keep a torsional gate closed? All those types of things can be calculated now with this simple set of equations. And it is as simple as that, all right? So for example, if I wanted to do, work an example here then. So everyone have those? Okay. Example. So if we have a dam, so let's say the dam comes down vertically and then it's sloped here 30 degrees off of the vertical. And down here we have a butterfly valve. And a butterfly valve is simply, it's like a plate, a flat plate that has a shaft going through it. So if we have a round pipe, and we put a plate inside that would block the pipe, so it's perpendicular. It's the exact area that would block the flow in that pipe. And I put now a round shaft through that plate. I can now rotate that plate, and when it is parallel with the flow is going to flow past it. When it's perpendicular to the flow, it's going to shut it off completely. And when it's partially, the flow is going to go around the cracks and go out. So I can control the flow with what's called a butterfly valve. It's a very common valve that we use for flow, usually for flow off and on, but sometimes it is used for flow control. So I'm going to draw that, see if this shows up a little differently as I put this in as red. And there's my big shaft in the middle. That actually shows up as red if I make it darker. Okay. Now let's give some dimensions to this. So we have a water level up here. There's our water level. And we're going to say that the centroid of that valve is 30 feet underneath the surface. And it feeds into a 10-foot diameter pipe. So it's a pretty good sized valve. And of course, that round part right there is the shaft. That's what rotates around it. And we want to find the torque on the gate in the closed position. So if we're using the shaft to hold this butterfly valve closed, we don't have any kind of a stop there, what kind of torque is required to keep from opening it? The first question, let's ask ourselves, why would it open? All right. If I have this butterfly valve in there and I have no torque on that shaft, would it open? And if it does open, why would it open? What's the principle that would force it open?
There's more pressure on the bottom half of the valve than the top because it's deeper in the water.
Good, yes. Remember, pressure increases as you go deep. So higher pressure on the bottom and on the top, so that thing's just going to rotate, okay? So in order to keep it closed, I have to have the torque on it. I have to have a moment. You know what torque is, right? Remember torque from mechanics and materials, a special moment, like when you're holding hands with your significant other, special moment. Sorry. So it's a special moment, so we want to calculate that to keep that closed and figure out what that is, all right? So we'll go ahead then and solve this, or solution then. And do some basic calculations here. We know that the total pressure force, pressure force is equal to gamma HC times A. Okay, so my pressure force then is going to be gamma, and we're going to, since this is water and we're dealing with English systems, 62.4 pounds per cubic foot. All right, HC then is 30 feet, and our area, because it's circular, is pi divided by 4 times 30 feet, or I'm sorry, 10 feet. So let me just take a quick break here, because if you hadn't had me for fluids, you might be saying, no, the area is pi r squared, right? Which it is. Area is pi r squared for a circular object. But in this class, we're dealing with pipelines. We don't go down to Home Depot and say, you know, give me a one inch radius pipe. We deal with diameters. So typically we know that the radius is equal to the diameter divided by 2. So pi times then d divided by 2 squared, which simply becomes then pi d squared divided by 4. So that's the equation that I'm going to use in this course, because 99% of the time we're talking about the diameter of a pipe or the diameter of a round area. In this case, it's a 10-foot pipe. So pi divided by 4 times 10 feet squared. That's, sorry, I've got my squared down there a little small, so make sure you get that little square right there. Okay. So now I can go ahead and calculate that. And when I calculate that, my pressure force then becomes 147,026 pounds. Right? So that's my pressure force, simple enough. And now I say, well, where's it acting at? Okay, now I forgot to put one thing on my free body diagram here. This angle right here is 30 degrees. Okay, that inclined slope coming down is 30 degrees off of the vertical. And you'll see why that's important. All right. So now I've got the magnitude of my pressure force. I have to find the location of my pressure force. So the location of the pressure force then, as we know, L sub P is equal to L sub C plus area moment of inertia, I sub C, divided by L sub C times A. All right. So first off, we need to determine what is L sub C. Now remember, L sub C is the distance along the inclined plane. So if I bring this back up here to where it intersects my free surface, L sub C then is going to be the distance along that inclined plane. I didn't draw that very well, did I? You get the point. This is L sub C. And so I know that L sub C is equal to 30 feet, because this is 30 feet down here. So it's like a little triangle, if you will. All right. This is 30 right here, 30 degrees, 30 feet. That's actually poor. I should do an example where I change one of those, right? So 30 degrees and 30 feet, we don't have those, but I want to know L sub C right here. So I'm going to just say 30 feet then divided by the cosine of 30. Cosine of 30 degrees now is going to give me L sub C, right? Cosine is adjacent over hypotenuse. So when I go ahead and do that calculation, then I get 34.6 feet for L sub C. So L sub C, the distance along the inclined plane, so from the top of the water down to my centroid of my gate, is 34.6. It's actually 34.56, but we just rounded off 34.6 feet down to the centroid. Now I have to find where L sub C is. Where is my pressure force? I'm sorry, L sub P. So I know the distance. Now I want to find L sub P. Scoop this up here a little bit. So L sub P then is equal to 34.6 feet plus I sub C, my area moment of inertia, and the area moment of inertia for a circle. I would, you'd pull out your old statics book if you wanted to. You'd note that. I'll note that over here. The I sub C for a circle is pi times r squared divided by 4. I don't have this one memorized. That is correct. Okay, r to the fourth divided by 4. There we go. Okay, so here's one of those times when I have to convert diameter back to radius. So this is going to be pi divided by 4 times 5 feet raised to the 4th divided by the distance to the centroid, 34.6 feet, times then the area, which is pi divided by 4 times 10 feet squared. And when I do all those calculations and I crank this out, I'm going to find out that L sub P, L sub P is equal to 34.78 feet. Okay. How's the sound coming through online today? Scott, is it working a little better or is it about the same?
Yeah, I can hear you okay. I haven't had to crank my volume up all the way.
Good, good, wonderful. You just might have to remind me every time to go in and change that because it probably falls back to some default. All right, so now where do I take this problem from here? Okay. Well, if I go ahead and draw now, kind of like another free body diagram. Okay, I'm going to slide this up here. And I note that I have my gate. And I have acting on that gate now this force right here of 147,026 pounds. And the distance that is acting off of that shaft is the distance between what? I don't put my force exactly on the shaft because it's not acting at the centroid. It's slightly off. So how do I find that little bit of distance right there? I want to find this distance right here.
L sub C, or L sub P minus L sub C.
Yep, that's going to be L sub P minus L sub C. Great. L sub P goes down to where it acts. L sub C goes to the centroid. Take the differential, and I have that little piece there. So it's the difference between 34.78 minus 34.6. Okay, and I find out that that little piece there is 0.18, right? Yeah, 0.18 feet. So now that I've solved all my pressure equations, what's left is just a hydrostatic equation. It's pretty simple. Laura?
Oh, no.
Oh, okay. So I know that now if I take the sum of the moments about the hinge and they have to be equal to 0, I should, that's not a very good free body diagram, I should actually apply a torque. And the torque to keep this thing closed is going to have to act in the opposite direction to keep that bottom from rotating. So we're going to call that T sub H, so the torque of the hinge. So, and if I use the standard notation of counterclockwise being positive, then I'm going to have 147,026 pounds multiplied by 0.18 feet minus T sub H equals 0, because it's static. So now go ahead and solve for T sub H, and I find that T sub H then is equal to 26,465 foot-pounds. That's the kind of torque I have to apply to keep that in place. Any questions on that?
This has more to do with gate design than anything, but wouldn't it just be better to have the shaft that operates the butterfly valve be oriented in more of a vertical direction so you didn't have to keep any constant torque on it to keep it open? Then you would only apply a torque to open and close it?
So let me think about that for just a second before I make some rash decision here. I think generally speaking, from a operational viewpoint, that may be correct. From a simply, yes, we need to operate the torque of that valve. However, so you're absolutely correct, Scott, on that, but okay. But these butterfly valves are not always static. So if it was a simply open close, we also have to take into account the fluid velocity coming out of the pipeline. And if we're taking this pipeline out of the dam and we have to go vertically down first and then turn an elbow, at those kind of pressures, we're likely to get really high velocities, which means we're very likely to get cavitation in our pipeline. Cavitation in the pipeline means that we'll start eating away at the dam and there's potential failure. And then the second part of that is that we only looked at one scenario with the, one scenario with the gate fully closed. We also have to look at now what is the scenario when we start to open the gate and we start getting a dynamic situation. In a dynamic situation now, we have fluid going around the top and fluid going around the bottom, and we can get negative pressures on one side than on the other side. So it's not as it's not as cut and dried as this simple equation for all conditions that may operate the gate.
Is that why most, like, I would say canals and ditches have like a slide gate?
Okay.
You're not opening and closing, you're just pulling it up and down, and there's always constant pressure on them. I guess the gate's not really.
Yeah, so this also gives me an opportunity for those online. Did you hear that question?
Faintly, if you could repeat it, that'd be great.
Okay, yeah, and that kind of helps me know because that's the kind of farthest seat, if you will. Well, maybe not quite, but pretty close. So the question or statement was, is that why in canals, open channel flow, why the sluice gate is generally vertically aligned? And so it's a constant pressure. And I would say that in canals, the sluice gate is more, I mean, that's more operational too, is because you create the smallest area when you're going vertical versus if you're trying to do incline. And that does create, the vertical actually only creates a pressure force rather than weight force. And there are operational issues if you try to do it at the angle. So yeah, they're kind of related, but not entirely. But yeah, I'm glad to see that you're actually thinking about applying these principles and how, and could we fix this? Could we make it better? Or, you know, because that's how better solutions come about, right? But understanding that there's a full range on all these things, you need to consider that can also change the design, because we don't always just design for one parameter. We have to design for the parameter across the whole scenarios. And in this particular case, the change in direction, if we went vertically down and then shot out, cavitation would be a big concern, and that would not be allowed in that scenario. Okay.
So is this pretty standard in an actual dam, this type of valve? Is that what they use most of the time?
So the question was, is this type of valve pretty standard in dams? And the answer to that is no. If you get really high head dams, what do I mean by high head? Well, that's high head is somewhat subjective, because some dams, you know, will only be 10 feet deep, and other dams are 300 feet deep or more. In fact, what's the deepest or the second deepest dam in the United States? Anyone know this?
I would guess that one.
I don't know. There's maybe it's Dorshak, which in Idaho. I'm not probably saying that right, but that's supposed to be one of the highest as well. I think it's like the second or something, but it's not a very big dam, but it's very deep. And it's not in the world. There's some that are way more deep. There's one down in Brazil that's like 1,000 feet or something. But anyway, when you get down to those kind of pressures and you put a valve on the bottom, no, then you need special kind of valves even if they're properly aligned, they start to cavitate. And so they have valves, what do they call those? They used to use Bunger-Howell valves, but those had problems too. And it was basically it was an opening and a needle. And the needle's really big, but the needle would, well, it was like a cone shape with a needle, and the needle would move back. So when the needle was shoved up against that cone, it was completely closed. And then when you pull it back, then the water could kind of go around it, and it was almost like excuse me, like a venturi. But there was a cone in the middle. But they've since changed over to what they call sleeve valves, which is essentially a pipe with a bunch of orifices, holes, they call them orifices. But so imagine, if you will, you took a pipe and you drilled just a whole bunch of tiny little holes in it. And then you take another pipe that's just the right size and you slide it over the top of it. And when that pipe on top of it completely slides over it, everything's closed. And as you want more flow, you pull that back, and then the flow has to go out all those little tiny holes, and it goes out into a chamber. And those valves do cavitate, but they cavitate away from any material, and so it doesn't hurt anything. And that's one type of valve. And then there's another specialty valve. I can't even remember. It's been years since I've even seen one of these things, but it's like a bunch of little plates. Anyone in here work with filter discs? Or I should say disc filters? Okay, so you've done some work with disc filters. Okay, the concept where if you want to filter water and you don't, how do you describe a disc filter? I mean, it's just, you got these discs that are stacked on top of each other, and they've got lines in them. So the water can move through the little lines to the inside. And then if you need to clean this thing, you just expand it, and the discs open up, and any material that's stuck in them just falls right out. It's kind of a cool little concept, actually. So they've used that same principle for these high head valves, to where these discs have like teeth around the entire side, and the teeth mesh with each other. And so when you to open the valve, you start to open it up, and those teeth get farther and farther apart. Well, and the teeth are arranged in such a way that the teeth on the outside are bigger than the teeth on the inside. Or when I say bigger, they're more separated. So and the flow tries to move around this tortuous path of those little teeth. It creates little head drops, little pressure drops rather than a big pressure drop, and hence then it doesn't cavitate, because it takes the pressure down in steps. So probably more than you cared to know, but that's and then there's a few other valves, but for a low level outlet dam, so let me back up. For a dam that's not very big, not very tall, and you have a pipe that you may want to use to drain it, that's what we call the low level pipe. It's like, we need to drain this, open that pipe up. That would be a common scenario, but the dam couldn't be very big. 30 feet would be pushing it, actually. Okay. All right. Other questions or comments? Okay, let's review another special principle that's part of hydrostatics. This derivation is actually pretty easy if you want to go back and look at your fluids principle, your fluids book. I'm not going to go through the derivation. We're just going to talk about the principle itself. Buoyancy. Okay, so the principle of buoyancy. Here's a little question for you. I have a cup of water, and I have a single large ice cube in that water, in that cup. Okay, when the ice melts, does the water level go down? Does the water level go up? Or is there no change in the water level? So A is up, B is down, and C is no change. So we had a few that said no change. Anyone else want to chime in their vote?
Well, I know that there's air in the ice, but being that the ice is above the water, you would think the level would go up.
Okay. There's air in the ice. How did the ice get air in it? When it froze? Okay. What if I told you there was no air in this ice? And then there's ways of doing that. There's ways of actually getting ice without any air. And I'm not going to dispute that large blocks of ice can have air in them. But let's say we get all the air out, so it's solid ice. When it melts, up, down, no change. And Samantha, you're thinking that the water level would go up. Okay.
I'll say it goes down.
You say it goes down. Okay, we got the range covered here. All right. What? Yeah. Okay. Okay. So, so Samantha, your reasoning, if I understood you correctly, you said the ice is above the water, and so when it melts, it's got extra fill in there, if you will, right? Okay. And if it goes down, what's the rationale to that?
When water freezes, it expands, and so the volume displaced is bigger than when it melts. Like once it melts, it'll be less volume.
Okay. And those that said there was no change, what's the rationale?
Water is water, and so it would float higher than what is it melted, it wouldn't displace more water than what it is.
Okay. All right. What? Go ahead.
I was gonna say, if the ice melts, the volume of the ice is smaller, so then it would raise up in the water, which is why the water level would drop. There'd be less displacement underneath the water surface.
Okay, so say that first part again. Because the volume of the,
When the ice melts, its volume gets smaller.
Okay.
then-
when the ice melts, its volume gets smaller.
So then it would raise up and make the water level drop.
Okay. All right. So we've got a whole range of concepts, and we're kind of all dancing around the same thing, the same principle. And I think you understand that ice is the density of ice. We talked about specific mass density and specific weight, but is the specific mass density of ice greater or less than liquid water? So is rho of ice less than, greater than, or equal to rho of just, let's say, water, H2O, even though this is water too, but this means liquid.
It's less.
Okay, we got a vote here that says less. Anyone want to dispute that? We got a few people, I can't see your faces very well, but some of your eyes are like, I'm not sure I buy into that. We're comfortable with the fact that ice weighs less, that the specific density, the total mass per unit volume is less for ice than it is for liquid water, right? That's why it floats. You comfortable with that? Okay. So, if that's the case, then what is the total weight pushing down on this ice block versus the weight that's pushing back up on it? All right, think about it. Okay.
I was under the impression that the reason like ice was like changed when it froze is because the like oxygen in it expanded, and that's what made it like float the air.
Okay.
So if it had no air, wouldn't that change that?
No. Because there's another principle at play here. When water freezes, and say when ice freezes, but that wouldn't be appropriate, right? When water freezes, it creates a crystalline structure that is actually less dense than the liquid itself, than the water itself. And that's not necessarily true for all solid liquid gas relationships, okay? But it's this crystalline structure, and it's actually a wonderful thing when you stop and think about it. You think, wow, that's pretty amazing. Pretty amazing that water is a special fluid. You say, why is it special? Water is water. Well, if water did not, if ice did not float, what kind of ramifications would that have? the fish in the wintertime wouldn't be very happy, would they? Because the cold air on top, ice freezes, sinks to the bottom, next layer sinks to the bottom, next layer sinks to, pretty soon the fish's got nowhere to go. In fact, he's gonna be trapped between this layer of ice and this, you know, and so we would have no fish in our ponds and lakes, or streams. If they keep flowing would be okay, but anything that freezes, we would have no fish because they would sink to the bottom. And only that, there'd be a lot of places that it would never thaw, would have permafrost. If you're familiar with permafrost, if you've lived way up north, permafrost is where the cold goes so deep down the ground, everything freezes, and even during the summer months, it does not thaw out. You dig down the ground, you still hit frozen ground, okay? We would have permafrost farther down because the cold wouldn't do that transfer system. So it's actually a pretty amazing thing in nature that occurs, all right? But, so if I take a volume, well, let's bring up this principle here. So the buoyancy force. Buoyancy force is gamma of the displaced, or gamma of the displaced fluid. So let's put gamma times the volume. Okay. So gamma, so the buoyancy force acting on an object is equal to the specific weight of the fluid that we're in. So that's why I didn't put D there. This is water times the volume that has been displaced. All right. So what's holding this ice up? Well, the ice block has a force acting down on it called the weight, and the water itself has a buoyancy force acting it up, and it's perfectly stable in this position because the buoyancy force is equal to the weight force. But the displaced volume of the ice is less because that only goes up to here. So I would suggest that if I had some way, you know, if I had a lightsaber that could actually cut out a chunk of water and the walls would stay perfectly vertical and I have a flat bottom. So I take the water out below this dashed line, okay, that is in perfect equilibrium with the water around it. It's in perfect equilibrium. It's not moving. This is a cup of water. So if I cut out this chunk of water, I have a given mass. If I take that mass and freeze it, well, now the mass density actually increases. I'm sorry, the specific mass density decreases because the volume increases, right? But has the weight changed? Weight doesn't change at all. I have the same amount of mass, the same total mass. My specific mass density has changed because my volume has changed, but I have the same mass. And since I have the same mass, I have the same weight. So after I freeze that, I can bring it back and place it right back into that hole. And it's going to provide the same weight down to the bottom of the water. And the water is going to push back up on it. But because it has a larger volume, it's going to stick up above the top of the water. Okay. So given that, the correct answer is, assuming that there is no the evaporation. If we get down to the physics, the physicists will tell you, you know, you're going to have water evaporate over the hour or two that this occurs, and the evaporation then is going to lower the level, right? But minus any evaporation, there's going to be no change.
So we're saying, are we saying the ice melts, or are we taking out the ice cube?
We're saying that if the ice melts, in this scenario here, if we wait until the ice melts, there's going to be no change in the water level.
Okay, I was thinking we were taking it out.
Oh, I'm sorry. Okay. Yeah, if we pull the ice out, then yeah, the water level drops. Yeah, that's exactly right. But I'm saying if we leave the ice in there and let it melt, there's going to be no change in the water level. Okay. Because it's the same total mass in that ice cube, because the weight force and the buoyancy force you have to balance each other out. So what's pushing down on the water is the ice, and what's holding the ice up is the pressure force pushing it back up, and those two are perfectly balanced. So if I melt that ice cube, they still have to be perfectly balanced. So it's going to be a level cup.
If it was like a different, if it wasn't ice, but if it was like something else, it would change the water level.
If the ice was something else,
If it was like a different liquid.
yes, if it was a different liquid, then it would indeed change. Oh, wait, would it? If it was a different liquid, yes, it would.
How would it affect it if it were salt water?
The ice would melt faster. And the answer is it would change too, because now they're two different densities. If it's salt water and the ice is just pure water that's been frozen. Yeah, so now we have two different densities. And so the force is going to be different because this gap right there now would be the gamma of salt water. And that would change things. Yeah. Okay.
But you said your reason was because the mass, overall mass doesn't change?
Correct. The total mass.
But if it was a different liquid, the total mass would still be the same, that's the whole thing, or no?
The total mass would be the same. Well, here's the thing. If it's a different liquid when it melts, if it's lighter than water, well, it's got to be lighter than water, so it's going to float on the top and then it's going to spread itself out. So let's look at this really fast. So let's say we had, I don't know, so the weight's going to be the same. So if I have something that's really, really light, somehow I froze a chunk of oil. And that oil then is going to be higher up out of the water because it's less dense. And now when it thaws, it's going to spread out to this scenario where there's going to be a layer of water, and there's going to be a layer of oil. Okay. And because it's less dense and it spreads itself out, I still say the water level is going to change. I have to sit down when I'm not under pressure. You know, it's really interesting when you're up in front of a class. The brain doesn't work quite as fast sometimes. It kind of reminds me, we aren't out of time, are we? Holy cow, we are. All righty. Well, so the buoyancy force, really quickly in here, the buoyancy force is that equation right there. So knowing the buoyancy force, now we can now apply that to fluid principles as part of statics and solve equations that include hydrostatics. Okay. Now remind me sometime if you want to hear the story about why it's different up here than being down there, and I'll tell you the story about that. All right. So have a great day. We'll see you on Friday. I'll post homework today, and then I'll be due Friday.
I'll see you tomorrow.
Yes. Have you set a time?
No, we have not.
Okay. Let me look at my schedule, and I'll send you an email.
Okay.
Okay. Thank you.
Bye.